This is the second lesson of a topic titled Linear and Quadratic Functions and Models. Lesson 1b focuses on quadratic functions and models. We'll learn about quadratics and their transformations, including standard form and vertex form. We'll also learn about freefall motion and how to model data using a quadratic function. I'm Mr. Stark, and this is Polynomial and Rational Functions. Let's get started. We'll learn about quadratics and their transformations in three parts: the transformation, vertex form, and an example that connects the two. For the transformation, let's go over how we would transform a basic function like f of x equals x squared to get g of x equals 2 times x minus 2 squared plus 3. The first thing to note is that the function can be rewritten as g of x minus 3 equals 2 times x minus 2 squared, so that the translations can be understood in the same way, an opposite way. Let's try to identify all three transformations. Notice that the 3 is affecting the g of x, which is a y value, so that's going to move the curve up by 3 units. There's a 2 on the inside of the function, so it affects the x value. It moves the curve to the right 2 units. The other 2 is on the outside of the function, so it affects the y value. It stretches the function by a factor of 2. In the last unit, we learned that transformations happen from the inside out. First, a horizontal translation to the right 2 units. Then, moving outward, a vertical stretch by a factor of 2. And finally, a vertical translation up 2 units. The next thing we'll do is learn about vertex form and how to find the vertex of a quadratic. If f of x equals ax squared plus bx plus c, the standard form for a quadratic, then the vertex form is f of x equals a, it's the same a, times x minus h squared plus k. Like I said, both a values are the same, and h comma k is the vertex. But the question is, what is h and what is k? How do we find them? Here's how. H is equal to the opposite of b over 2a. So negative b divided by 2a. You might recognize that from the quadratic formula. The opposite of b plus or minus square root of some stuff divided by 2a. But I'm not going to get into why that is right now. The k value is found by plugging h into the function, so f of h. Oh, and one more thing. When you graph quadratics, you get parabolas, and parabolas have an axis of symmetry that goes through the vertex. The axis of symmetry in this case is x equals h, which is a vertical line. Now I'll demonstrate how to find the vertex and the vertex form of f of x equals 2x squared minus 8x plus 11. Notice that a equals 2, the leading coefficient, b equals negative 8, and c equals 11. Therefore, the h value is the opposite of negative 8 divided by 2 times 2, which is 8 divided by 4, which is 2. Plugging 2 into the function, we get k equals 2 times 2 squared minus 8 times 2 plus 11, which is 8 minus 16 plus 11, which is 3. So the vertex is 2, 3, and we could rewrite our function as f of x equals 2 times x minus 2 squared plus 3. Hey, that's the original function we started with in the transform section. I hope you could see the value of having a quadratic in vertex form. We can sketch the parent function x squared, then this function using transformations. We also know that the axis of symmetry is x equals 2. In topic 3, we'll learn how the a value affects whether the parabola opens upward or downward. The other method that can be used to write a quadratic in vertex form is completing the square. But the opposite of b over 2a trick is so great, and now is just not the time. Now let's talk about free fall motion, because it could be modeled by a quadratic function. Consider throwing or dropping a tennis ball. And feel free to do it if you have a tennis ball handy. The position of that ball could be modeled by the function s of t equals negative 1/2 gt squared plus v sub 0 times t plus s sub 0. Whoa, 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 that's a lot of stuff. S stands for spatium, which means position or distance in Latin. T is time, g is gravity, v sub 0 is the initial velocity, and s sub 0 is the initial position of the ball. If you simply drop the ball, the initial velocity is 0, but many times we throw it. The acceleration of gravity is 32 feet per second, or 9.8 meters per second. That means the position function of a tennis ball in meters would be negative 4.9 t squared, 1/2 of 9.8, plus v sub 0 t plus s sub 0. Let's suppose the data to the left was recorded when a tennis ball was tossed straight up. We can use that data to find the position function of the tennis ball and practice using the regression features on the TI-84. Let's do it. If you have a TI-84 graphing calculator, you should follow along. Otherwise, sit back and enjoy the show. Let's enter our data using the stat edit feature. Notice that I already entered the data, so you could use this data to enter it yourself. And sorry about the decimals, we're modeling the height of a tennis ball, so it's pretty dicey. Let's turn our stat plot on. Second y equals, press enter, and enter again. You could change the color or the marks if you like. Then let's do zoom 9. What that will do is automatically change the window based on your data. And we can see that that data is modeled by a quadratic function, or it has a parabolic shape. So that's why we would choose quadratic when we go to the models. So let's do that. Arrow right to calc, and then we'll go down to quad reg for quadratic regression. Press enter, and let's store the regression equation in y1. Alpha trace, enter, enter. Notice that this is a quadratic function in standard form. A is negative 4.7-ish, and recall from our model that the coefficient was negative 4.9 in terms of meters. So it's pretty close. You know, there could be some errors in measurements and stuff like that. The b value in this case is the velocity at which the tennis ball was thrown up. So it's a positive value, so it's being thrown up 3.7 or 3.8 meters per second. The c value is the height at which the ball was thrown up. So that was 1 meter or 3 feet tall or so, you know. So maybe it's tossed up underhand or something like that. So we could press y equals to see that entire function. It gets a little crazy, lots of decimals. But if you want to see the end, you could press second right. And you could see that that initial position is 1.0 something meters. So we could press graph now. The window is already set from our data, and we could see that the model is a good model. It's a parabola, and it goes through all of the points. So that's pretty great. So the other thing that we can do is, let's say we wanted to find the max of the ball. We could press trace. We're on plot right now. All we have to do is press up or down. And it just kind of made me jump to the right there. So now if I want to find the max, I'm looking at the y value, and I see that it is 1.8. We could do that officially by pressing second trace 4. It says left bound, move to the left, enter. Right bound, move to the right, enter. And this little machine needs you to go close to it, just in case there are 2. Press enter. And we were pretty much correct before, so this was just another thing that we could try. One other thing, if you're trying to project the data, you could plug in values. So let's see how far these values go up. I don't quite remember, so bouncing around here, sorry about that. But notice that the x values go up to like 0.9 basically. So those are as high of the values that you could enter, 0.89-ish. So let's press second trace value, and let's say I want to find out where the ball was at a half a second. 0.5. Aha! So at a half a second, the height was 1.76. And I could plug in all sorts of numbers as long as they're in this window. One more thing you could do, I might as well show you. You could enter any value here. So you could press alpha trace, y1, and plug in certain values here. So let's do 0. Let's actually do 1 second, because that wasn't on the actual screen. So you could do it here. 1 second, the ball is at a height of 0.13 meters. And so you could actually play with a bunch of values and see if you could get it to 0 just by plugging in larger values like 1.1, 1.2, or something like that. There you have it. We modeled data using a quadratic function. And that is the second lesson of the polynomial and rational functions unit. I'm Mr. Stark. Join me for the next lesson, lesson 2A. Did you press that subscribe button yet? Give me a thumbs up if you liked the video. If you have a question, you might as well ask it. Do you have a comment? Feel free to add it. Hey, thanks for watching.